Hi, everyone. My name is Tian. I'm a PhD student working with Professor Kunlei at Stanford University. In today's talk, I plan to cover the design considerations for serving recurrent neural networks efficiently with a spatial accelerator. First, RNNs are popular data center workloads. According to the numbers showed by Google, in the year of 2017, about 29% of the in-data center machine learning workload are RNNs. A natural question to ask is how to design an efficient hardware accelerator for all the RNN kernels. Or more specifically, we care about designing such an RNN serving hardware that can achieve high performance with high efficiency measured in terms of performance per area and performance per watt. However, the hard truth is RNN is hard to serve efficiently for the following two reasons. That first, RNN kernels contain complex data flow, which is hard to serve efficiently on the modern hardware. And the second challenge is that RNN sizes can vary a lot over different problems. To get a sense of how complex a data flow within an RNN kernel would look like, here is an example of the data flow path within a long short-term memory cell, which is one flavor of the RNN kernels. This kernel contains 4 weight matrices of size d by h, where d is the number of input features and h is the number of hidden units. It also contains another set of 4 weight matrices of size h by h, and 4 input vectors of size h. Oops. During execution, the RNN kernel first consumes an input vector, a hidden vector, and a memory vector. At the end, it generates 2 new memory vector and hidden vector. The execution of this data flow can be divided into 2 parts, where the first part contains 8 matrix vector multiplications, and the second part contains 13 element-wise operations. As you can see in here, the data flow of this RNN kernel is quite complex. The second challenge is that RNN sizes can vary over different problems. For example, in this table, I show 2 tasks, where the first task is a sequence classification task that uses an RNN of size 128. The second task is a speech recognition task that uses an RNN of size 2816. And as you can see in here, the large task can be 20 times bigger than the smaller one. And as a result, it is hard to find a serving platform that can achieve high hardware utilization and energy efficiency on both sizes of these RNN tasks. So in short, RNN is hard to serve efficiently since their kernels contain complex data flow, and their sizes has a very large variation over different problems. To deal with this complexity, most software frameworks and hardware accelerators choose to decouple an RNN kernel into a set of basic linear algebra subprograms, or also known as the BLAS subroutines. For example, in the context of inference, the brainwave neural processing unit from Microsoft chooses to accelerate the matrix vector multiplication operation within the RNN kernel, which is at BLAS level 2. In the context of training, the tensor processing unit from Google chooses to accelerate the matrix-matrix multiplication operation, which is at BLAS level 3. Hence, a natural question to ask is if BLAS is the right ISA for accelerators. From a very high-level point of view, using BLAS abstraction enables the software developers to focus on the very high-level functionality of their applications without worrying about the actual hardware implementation. Similarly, the hardware developers can focus on implementing highly optimized BLAS kernels. However, individually optimized kernels do not guarantee globally optimized end-to-end application. Now, let's zoom in to the inefficiency introduced by using BLAS abstraction when serving an RNN kernel. First, let's look at the matrix vector multiplications in this RNN. The size of the matrix is h by h, where h is the number of hidden units, and the size of the input vector is h. A BLAS accelerator usually blocks on both dimensions of the weight matrix. In this example, I show a BLAS accelerator that can complete the matrix vector multiplication operation in 6 iterations. And as you can see in here, this BLAS accelerator is underutilized due to misalignment on both dimensions of the weight matrix. To give a more concrete example, let's say that the BLAS2 accelerator can consume a submatrix of 60 by 80 per iteration, and it is trying to serve an RNN of size 128. For this example, the utilization is only at 56%. Moreover, the intermediate result coming out of this accelerator is in the form of vectors, which needs to be buffered into on-chip Scratchpad memory. And on-chip Scratchpad memory is a very energy inefficiency component. When we zoom out and look at the overall data flow, we'll see that there are 26 paths in this data flow that requires frequent access to the on-chip Scratchpad memory. From this example, we show that BLAS abstraction would lead to hardware underutilization caused by misalignment. And alternatively, we can use a more general abstraction, which is the loop-level abstraction. The loop-level abstraction allows us to perform fine-grained tiling along one dimension of the weight matrix. As a result, the size of the intermediate result coming out of this accelerator is 1, which means that the element-wise operations that comes in the second part of the RNN kernel execution can now be fused into the matrix vector multiplications. Moreover, when executing the matrix vector multiplication operation, the accelerator that supports fine-grained tiling only suffers from hardware underutilization from one dimension of the weight matrix. If we were to reuse the same example of serving an RNN of size 128, this time the utilization can be as high as 80%. Moreover, the output can all be buffered into an on-chip register, which is more energy efficient compared to the on-chip Scratchpad memory. From a high-level point of view, the fine-grained tiling happens along the hidden unit dimension, which means that within each tile, the weight matrix is now converted into a weight vector of either size h by 1 or d by 1. And then we tile it by h times to create the output vectors. Now, with fine-grained tiling, the matrix vector multiplication operations within the original data flow graph are all converted into dot products. Moreover, the 26 paths within the original data flow graph are now only accessing on-chip registers instead of the on-chip Scratchpad memory. Overall, we find that loop abstraction enables fine-grained tiling to reduce hardware underutilization due to unalignment and to reduce the size of the intermediate buffers. Second, in this talk, we show that BLAS abstraction will lead to a heterogeneous accelerator design that would contain unbalanced pipeline when serving RNN tasks of different sizes. Let's first think of an RNN serving task from a very high level. The first part of an RNN serving task contains matrix vector multiplications that requires computation of big O of h plus d multiplied by big O of h, where h is the number of fitting units and d is the number of input features. The second part of this serving task contains element-wise operations that require big O of h computation. If we were to stick with the BLAS abstraction, when designing the accelerator, we'll need to have dedicated hardware unit to support the matrix vector multiplication subroutine from the BLAS. And we would also need to have dedicated hardware unit to run the element-wise operation. In contrast, for homogeneous accelerator, we can have, say, a pool of computation units where each computation unit can be repurposed to perform either a matrix vector multiplication or an element-wise operation. Let's look at how a heterogeneous accelerator will handle the RNN serving task. When serving the RNN task, we can overlap the matrix vector multiplication with the element-wise operations. However, for a heterogeneous accelerator, the level of parallelism that the matrix vector multiplication unit and the element-wise operation unit is fixed during runtime. And as a result, when serving a small RNN task, the matrix vector multiplication unit within the BLAS accelerator would run for fewer cycles compared to the element-wise ones. In this case, the element-wise operation unit would become the bottleneck within the whole end-to-end pipeline. When serving a large RNN, the case is flipped in the sense that the computation requirement for the matrix vector multiplication operation grows at a much faster rate compared to the computation requirement for the element-wise operation. And as a result, when the size of your RNN grows, the bottleneck, the matrix vector multiplication unit will spend more cycles to run compared to the element-wise operation unit. And in this case, the bottleneck will be shifted to the matrix vector multiplication unit. In this example, we show that a heterogeneous accelerator will have an unbalanced pipeline with respect to different problem sizes. When serving the RNNs using a homogeneous accelerator, the pipeline can dually be balanced. For example, when serving a small RNN, a homogeneous accelerator can choose to reallocate more resource for the element-wise operations in order to balance with the matrix vector multiplications. When serving a large RNN, the homogeneous accelerator can also choose to reallocate more resource for the matrix vector multiplication in order to achieve a balanced pipeline. In this example, we show that a homogeneous accelerator can always achieve a balanced pipeline regardless of the problem sizes. To evaluate the strategies that we propose in this work, we choose 3 hardware platforms. The first platform is a Tesla V100 GPU that supports programming by using TensorFlow and cuDNN. The key operation that the GPU chooses to accelerate is the matrix-matrix multiplication, which is a BLAS level 3 subroutine. The GPU is a heterogeneous accelerator. Second, we choose the brainwave overlay architecture on top of implemented on top of a Stratix 10 FPGA. It is a heterogeneous spatial accelerator that focuses on accelerating the matrix vector multiplication subroutine, which is at BLAS level 2. Lastly, we choose a homogeneous accelerator called plasticine, which is also a coarse-grained reconfigurable architecture. It supports acceleration at loop construct level. All of the 3 platforms possess roughly the same numbers of peak 32-bit teraflops. Moreover, the plasticine CGRA is at an older generation compared to the Tesla V100 GPU and the Stratix 10 FPGA. Comparing to the GPU and FPGA platform, the CGRA platform uses a die area of 494. The Stratix 10 FPGA uses the smallest thermal design power. We run our evaluation by implementing the RNN kernels from the DeepBench benchmark. We implemented these kernels on Tesla V100 and on the plasticine CGRA. We collect the performance number of brainwave from their original paper. Overall, we find that homogeneous accelerator that supports more general abstraction at loop construct, such as a plasticine CGRA, can achieve very consistent and high hardware utilization across many different sizes of the RNN kernels. In contrast, a heterogeneous accelerator, such as brainwave, that supports only BLAS level abstraction, can only achieve the highest hardware utilization at a particular problem size, which is at GRU 2816 in this case. We were not able to saturate the computation capacity of the Tesla V100, since the size of a serving task is very hard to saturate as DRAM bandwidth. Overall, we show that a homogeneous accelerator, such as plasticine, can achieve the best performance and the best efficiency measured in terms of performance per area and performance per watt, comparing to the other platforms. In short, in this talk, we show that homogeneous accelerators with loop-level abstraction can achieve better hardware utilization and efficiency comparing to heterogeneous accelerators that only support BLAS abstraction. With that, I conclude my presentation. Thanks for coming, and I'm open for questions now.
We now have time for questions. When you have questions, please come to one of the microphones, introduce yourself, and ask your question.
Hi, Rick Haye with Microsoft. Very interesting talk. I'm curious on the GPU comparison, the V100.
Let me try to.
The V100 RNN numbers. I wonder if you used the latest CUDNN.
You mean the CUDA and LSTM implementation?
That's right, where they're doing some temporal unrolling and overlap of the
computation. Right. We actually use that implementation. And to be more precise, the CUDA and LSTM implementation tries to block on the element-wise operations within the original kernel. But then it still needs to trigger like memory transfer when you are trying to send the weights over. And in contrast, I think both Microsoft Brainwave and the CGRA that we choose, which is called plasticine, used low precision arithmetic and was able to embed all the weights on chip. And that's actually a key difference between the Tesla V100 implementation and our implementation, and of course Microsoft Brainwave's implementation. Questions?
Yusuf Clarkerman of Bloomberg. I was wondering if you tried with the V100 to do a custom CUDA kernels which did loop-based parallelization, if you think you would get better results, or? We
actually used the CUDA implementation for both the LSTM cells and the GRU cells. But I think if you look at the CUDA kernels for those two, like CUDA APIs, you will find that they're the first part of the RN kernels are still implemented using a streaming gem instead of using loop construct. And whereas in contrast, our implementation can fuse the loops in the first part and the second part.
Yeah, but the question is, if you use CUDA to do your implementation running it on a V100, what utilization do you think you would get?
I think we'll still get a very similar utilization as reported in here.
Thank you.
Okay, thank you.
I have a quick question as well. So the observations about LSTM are very interesting, but a lot of new workloads for machine translation start to use models like Transformer and BERT. that use attention layers and essentially better fit for GPUs. So what do you think any of your ideas will be applicable in this domain as well?
Sure. So I have 2 points for that. The first point is, I think for at least for like the models for like general transformers, it requires to send in like more time steps, whereas in contrast for most of RNNs, it only needs 1 time step in order to generate the next result. And therefore, I don't really, I think it would be quite hard, at least from a hardware architecture point of view, to have a very fast and efficient serving platform for a transformer-based model. This is my first point. And the second point is that if you look at the individual like transformer cell within the overall model, it actually contains a more simple data flow comparing to the LSTM ones. For example, if you look at, say, like one individual transformer cell, it's a matrix multiplication followed by a softmax layer, where the softmax part cannot be categorized into a BLAS subroutine. And in which case, the application that we use, the strategy, the fine-grained tiling scheme that we're using here can still apply to the softmax plus the matrix multiplication part of the transformer cell, which still, enables kernel fusion and other, and achieves a better pipeline.
Okay. Thank you.
Thank you.
Thanks to the speaker again.